Hello friends, I welcome you in lecture number 23 on vector calculus. In this lecture we will discuss this question on Green's theorem which was asked in GTU Summer 2019 exam. The question is, apply Green's theorem to find the outward flux of a vector field f bar equal to 1 divided by x into y times xi plus yj across the curve bounded by y equal to square root of x, 2y equal to 1 and x equal to 1. Here we are asked to find out the outward flux of a vector field using Green's theorem, and we know that if we want to find out outward flux of a vector field, then we will consider normal form of a Green's theorem. And first we recall what is normal form of a Green's theorem. Suppose f bar equal to m into I plus n into j be a vector field whose components m and n are continuous and they have continuous first order partial derivatives, and this vector field is given over some closed curve C which encloses some region R in the xy plane. Then the outward flux of this vector field along curve C is m dy minus n dx, and Green's theorem says that this outward flux is equal to double integral of divergence of the vector field f bar over this region R. And by the definition of divergence, if f bar is mi plus nj, divergence of f bar equal to partial derivative of m with respect to x plus partial derivative of n with respect to y, and then we have to integrate this quantity over region R. So here we are asked to apply Green's theorem to find out this outward flux. So we will not compute line integral, but we will find out the value of line integral using the double integral of del m by del x plus del n by del y over given region of integration. So first we write down what is given vector field. First we write that given that vector field f bar is equal to 1 divided by x into y times xi plus yj, and this we can rewrite as, therefore f bar equal to, we multiply this bracket by 1 divided by xy. So we have x divided by xy, and we can cancel out x provided x is non-zero, and plus y divided by xy, so y will cancel out provided y is non-zero. So this f bar is defined on the region R, which is bounded by these three curves. One is parabola y equal to square root of x or y square equal to x, and other two curves are lines. So we should check whether our vector field is defined over this region bounded by these three curves or not, or we should check whether f bar is defined along curve C, which is the boundary of the region bounded by these three curves. And if we sketch the region, first we require this two-dimensional plane. Suppose this is y-axis, this is x-axis, and we first write down y-axis, this is x-axis, and we have these two lines, x equal to 1 and 2y equal to 1, that is y equal to 1 by 2. So first we sketch x equal to 1. Suppose this much distance is 1, then this will be 1/2. Similarly, this distance is 1/2, this distance is 1. So first we sketch the line x equal to 1, which is at a distance 1 from the origin. So this distance is 1, therefore this is the line x equal to 1, and we require another line y equal to 1/2. So it is line parallel to x axis. So these are the lines. This is x equal to 1, this is y equal to 1 by 2, or we can write 2y equal to 1. This point is 1 by 2, here we have 1 by 2 0, this is 1, and therefore this point is x is having value 1, y is 1 by 2, and this much distance is 1 by 2. Now we have to sketch the parabola. Parabola is y equal to square root of x. So if we take intersection of parabola with this line x equal to 1, if we put x equal to 1, y will be 1. So this parabola will intersect line x equal to 1 at point 1 1. It will pass through this point 1 comma 1, and if we take y equal to 1 by 2, if we are interested with the intersection of y equal to square root of x with y equal to 1 by 2, we put y equal to 1 by 2, and we find that x equal to 1 by 4 by squaring on both sides. Therefore this parabola will intersect the line y equal to 1 by 2 at point 1 by 4 comma 1 by 2. So this distance is 1 by 4 and this is 1 by 2. So parabola will pass through this point also, which is 1 by 4 comma 1 by 2, and it is passing through origin also. So this is the graph of the parabola y equal to square root of x, and it is passing through these 3 points. We are just sketching roughly to get the idea, and this parabola is symmetrical about y-axis, so we will have mirror image below x-axis. Now what is the region bounded by y equal to square root of x? This is the line x equal to 1 and y equal to 1 by 2. So this region is bounded by these 3 curves: y equal to square root of x, y equal to 1 by 2, and x equal to 1. The lower region is also bounded by y equal to square root of x, x equal to 1, and y equal to 1 by 2, this region. But we will not consider this region because this region includes origin on its boundary, and our function f bar is undefined at origin. If we take y equal to 0, x equal to 0, f bar is undefined. So we will consider this region for double integral, and this is the boundary of the region, which is our curve C. So this is C denotes the boundary of the region R, and we are interested in the double integral over this region R. So our function f bar is 1 by yi plus 1 by xj, and if we consider this boundary, then our function f bar is defined at every point on this boundary, as well as it is defined at every point on region R. Okay, fine. So now we compare our vector field f bar with m into I plus n into j. Suppose this is equal to m into I plus n into j, then we find that m is 1 by y and n is 1 by x. M equal to 1 by y and n equal to 1 by x. And for double integral we require partial derivative of m with respect to x, but this is independent of x and we are differentiating with respect to x partially. Therefore y is considered as constant. Therefore partial derivative of 1 by y with respect to x is 0. Similarly, partial derivative of 1 by del n by del y, partial derivative of n with respect to y is also 0. We recall that Green's theorem says that this flux m dx minus n dy is equal to double integral over r del m by del x plus del n by del y. So we require partial derivative of m with respect to x. There is no x here, so this is 0. Partial derivative of n with respect to y, so this is also 0. So now we don't have to search for limits of integration also, because our function, this function becomes 0 at every point on the region. Therefore outward flux has value 0. So now we can directly write by Green's theorem, the outward flux is, by Green's theorem, the outward flux of vector field f bar is line integral m dy minus n dx, m dy minus n dx along curve C is equal to double integral over r del m by del x plus del n by del y. Suppose we consider integral first with respect to y and then with respect to x, and this function becomes 0 at every point on the region R. So we don't have to search for limits of integration of y and x also. We can directly put 0, and integral of 0 is 0. Therefore we find that outward flux is 0 using Green's theorem. So here it is not necessary to sketch the region of integration also, but we have sketched the region of integration to check whether our function f bar is defined at every point on the region as well as on its boundary. So that is the reason why I have sketched the region of integration. Otherwise, first you can decide what is capital M and capital N, and then you can evaluate partial derivatives and their addition. If this is 0, then you can directly write that this is equal to 0. The outward flux of given vector field along curve C is 0 by Green's theorem. So here we have obtained the outward flux of this vector field f bar across the curve C, and we find that it is 0. So whenever they ask to find out outward flux, we will use this normal form of Green's theorem, and whenever they ask to find out circulation of a vector field, we will apply this tangential form of Green's theorem, m dx plus n dy along curve C equal to double integral over r del n by del x minus del m by del y. So this gives us, this quantity is called circulation of a vector field. So if they ask you to find out circulation of a vector field, use tangential form of Green's theorem, and if they ask you to find out outward flux of a vector field, use normal form of Green's theorem. And if they simply ask you to evaluate the line integral, then you can use either tangential form or normal form. You will get the same answer. So this is all about this session. I hope you like it. Thanks for watching.